Welcome everyone. In this lecture, we will be discussing about the wave parameters for rectangular waveguide. The parameters that we are going to learn here is the propagation constant, velocity of the propagation, wavelength, the operating frequency and the cutoff frequency, the intrinsic impedance both for transverse electric and transverse magnetic mode, phase constant, the wave parameter. The most important wave parameter is the propagation constant. So as you know, the propagation constant gamma square is equal to h square plus minus k square, where h square is equal to kx square plus ky square, and kx is equal to m pi over a, and ky is equal to n pi over b, where a and b are the dimensions of a rectangular waveguide. So a could be the length of waveguide and b is the width of the waveguide. So now if you substitute kx and ky in the equation and solve for the propagation constant, we will get propagation constant is a square root of m pi over a squared plus n pi over b squared minus k is the wave number, and k square is equal to omega square square root of mu times omega square and times mu epsilon. K square is equal to omega square times mu times epsilon. Mu and epsilon is the permeability and permittivity of the dielectric material field inside the waveguide. Now the propagation constant would have the attenuation constant and a phase constant. Attenuation constant is the real part of the propagation constant and phase constant is the imaginary part. But if you inspect the expression of gamma here, you will see the m and n are the integer number, positive integer number called the mode of the waveguide, mode of operation for the waveguide. Pi also a real number. A and B are the dimensions of the waveguide. They are also positive and a real number. Omega is the frequency. This is also positive real number. Mu and epsilon also positive and real number. So the values that all of these parameters in this expression are positive and also real number. The square root of this cannot be a complex number, but it could be either a real number or an imaginary number depending on the frequency, because this frequency term omega square mu epsilon has a minus sign, so that is meaning that you have to subtract this value from these values. So if the product of omega square mu epsilon got lower number than these values, then the propagation constant will have a real positive number, a positive and real number, so that is equal to alpha. But that time there is no beta. And again, when this value omega square mu epsilon is higher than this value m pi over a square plus n pi over b square, then the square root will have a negative value inside the square root. Then the square root of minus 1 is equal to z. So that means you will come up with an imaginary number, but that time there is no real number. So if omega is higher then you can get an imaginary part or a phase constant part. But when omega is smaller or a small value, a low number value, then you can get a real part or the attenuation constant or the attenuation factor. So depending on the value of omega, we might say three cases. We might find three cases. But case A is the cutoff situation. That means if the omega has a value like omega square mu epsilon is equal to m pi over a square plus n pi over b square, then the entire things will be 0. So you will get gamma equal to 0. So both A and B will be 0 at this time. So the wave will not propagate, and this frequency is called cutoff frequency, or this mode is called cutoff mode. So at the value of this frequency, the waveguide behaves like a cutoff. So this is the threshold frequency. And if the frequency is lower than this, that means omega square mu epsilon part is smaller than m pi over this part, m pi over a square plus n pi over b square, then the value inside this square root will be positive, and you will get gamma greater than 0, positive number. That means this is a real value, gamma becomes real value, so wave will not propagate but attenuates. So at this frequency, the waveguide will attenuate the signal, so it will not propagate, the entire signals will die out inside the waveguide. And in case C, if omega is high enough that the product of omega square mu epsilon has the higher value of this number, then the square root of this will be negative. So you will get something negative here, negative, because this value is higher than this value, so you get some negative number. So you see the negative number, so negative sign can be replaced by a negative j1 and the square root of the number, and then negative 1 is equal to j and square root of this something, and this square root of something is equal to the b, so you will get j beta. So at this time you will get j beta. So wave has a phase constant but no alpha. So that means gamma becomes completely imaginary. So the wave propagates without attenuation. And from this we can say if the frequency is less than the cutoff frequency, the signals will not propagate. And if the frequency is higher than the cutoff frequency, then the signals will propagate. So the waveguide can be used as a high pass filter. So if you see the frequency response of a waveguide, so here if you vary the frequency until you see the gain or the signal will be attenuated at this stage, and then at the cutoff, that's the marginal frequency. So if the frequency is lower than this cutoff frequency, the wave will be attenuated. If the operating frequency is higher than this, then the wave will be propagating in the waveguide. So let's say this frequency, this is your operating frequency f. If f is higher than fc, the waveguide can F is higher than Fc, waveguide can carry this frequency or transmit this frequency. But if F is smaller than Fc, the waveguide will completely attenuate the frequency or completely absorb the frequency. So now from the cutoff frequency expression, We know that at cutoff frequency we'll get gamma equal to 0 and m pi over a square plus n pi over b square equal to the frequency. We write down omega c because for cutoff we use the suffix c. C is for the cutoff. Omega c squared mu epsilon e is the wave. So at this case wave doesn't propagate, but it is the cutoff or threshold point. And here omega we replace by omega c. Now at this case we can replace omega with 2 pi fc or 4 pi square fc square mu epsilon. Now if you solve for fc will be 1 over 2 pi this square root of mu epsilon m pi over a plus n pi over b, and 1 over mu e, that's the speed of propagation in the dielectric region. For example, let us assume this is your waveguide. This waveguide is the material. Inside the waveguide you have a dielectric material inside the waveguide. So the dielectric material inside this waveguide has epsilon and mu. If there is no waveguide surrounding this dielectric, then this dielectric will propagate the signals with this speed, mu u speed. So we are assuming the speed in the dielectric for the unbounded case. So if the dielectric material is not bounded by waveguide, then we will get the speed of propagation like this. So UU is called the unbounded medium speed. The medium with permittivity epsilon and permeability mu has a propagation speed UU if there is no waveguide present. So if the medium is unbounded or without boundary, you will get the speed like this. Now Fc can be written like this. We can cancel this pi with this. We can write down this, and we can further simplify this by taking alpha at the left. So you can write m square plus n square a over b square. Here m and n are called the mode number and a or b are the dimension of the waveguide. So let's say this is a and this is b. So for example, if you have a waveguide like that is operating in TE on zero mode, T0 on zero mode with alpha equal to 2 and beta equal to 1. So let's say 2 meter, beta equal to 1 meter. Then you can find the cutoff frequency putting m equal to 1 and n equal to 0. So m equal to 1 square, it will be UU over 2 times 2, 4. UU over 4. UU over 4 hertz. So this is how we can find the cutoff frequency. So that means if your frequency is UU over 4, let's assume you have a air-filled waveguide, then UU will be 3 times 10 to the power 8 over 4. That means 7.5 or 75. So 7.5 times 10 to the power 7. So that means it is 75 megahertz. So cutoff frequency is 75 megahertz, meaning that if your operating frequency is less than 75, that wave cannot be propagated through the waveguide. So your waveguide cannot carry the frequency or propagate or transmit the signals of less than 75 megahertz. But if the operating frequency is higher than 75 megahertz, that can be carried by the waveguide in TE10 mode. So let's say for TE10 mode, your cutoff frequency is 75 megahertz. So if you try to operate in this region, the waveguide will not work here, so it will not carry the signals. But if your frequency is somewhere here, the waveguide can carry this frequency in this mode, TE10 mode. If you have different mode, the cutoff frequency will be the different. But TE or zero mode is the dominant mode. That means at this mode you have the lowest cutoff frequency. Now we need to find wave parameters like phase constant. The phase constant beta, to find this beta, like say we know gamma has the expression like this, gamma equal to m pi over a squared plus n pi over b squared minus omega square mu epsilon. But if we assume that this value is higher than this value, then we'll get beta. So if you write gamma equal to z beta, meaning that you have to take negative sign out, and then the entire part will be omega square mu epsilon minus this. So now if you cancel this, square root of z is equal to 1 is equal to z, so you can cancel out this, you will get beta equal to this. So you will get beta equal to this. Now if you take omega square mu epsilon as a common factor, you get 1 minus this. Now you know omega equal to 4 pi square f square, and 1 over mu epsilon a is u squared, and I can take pi square as a common factor. So pi square is a m over a square plus n over b square. Now we have to remove this with respect to the cutoff frequency. For cutoff frequency, the expression we found before as u over 2 m over a plus n over b square. So now m over a over b square equal to we got 4 fc square over u square, and beta u, just we already know that beta u equal to omega mu epsilon e. So this part we replace with beta u. Beta u is the phase constant in unbounded medium. So if the waveguide is filled with a dielectric and that is unbounded, you know the beta expression we found for dielectric material, beta equal to mu over epsilon. So we obtained this equation for the perfect dielectric material. Now you replace the value for ma over nb squared here, and then simplify this, you will get fc square over f square, or you can write fc over f whole square. So this is the expression for phase constant in waveguide. So in waveguide, phase constant is equal to the phase constant in unbounded medium times the square root of 1 minus fc over f squared. The wave velocity, so we can find the wave velocity or propagation speed in unbounded medium as this expression. We already know this. This is for a perfect dielectric material. Now for we can also know the formula is for unbounded case. Formula is omega over beta u. So if you use the same formula for finding the phase velocity, so you look at phase velocity is equal to omega over beta. And this beta, basically we found the expression for beta is like beta u and 1 minus fc over f square. And fc over f square 1 minus fc over f square beta u. So omega over beta u is u and like this. So now if you inspect this value here, so it got fc minus f. F is the operating frequency and fc is the cutoff frequency. F has higher value than fc. So the number here must be less than 1, and the square root of fractional number will be even smaller. So you will get the phase velocity is u something divided by less than 1. So if you assume that u is 3 times 10 to the power 8, 10 to the power 8, and divide it something less than 1, let's say zero point 0.5 or zero point 0.8, let's say zero point 0.5, then this value becomes 6 times 10 to the power 8. So you see the speed of the propagation is higher than the light speed, and it is not possible according to the Einstein's theory. So the speed cannot be higher than the light speed, but we found that phase velocity for waveguide is higher than the light speed, but it is not possible. Basically, in the waveguide, the wave is propagated as a group, so we are looking for the group velocity, and group velocity times space velocity is u squared, or you can find group velocity is equal to u 1 minus fc over f squared. So the group velocity must be less than the light speed or light velocity. If you see the waves here, you can find there is a red. So you see the red peaks indicates the group velocity, and the other dots indicates the phase velocity. Red dots, when it travels from one side to other side, it passes two of this green. So that means the group velocity is one half of the phase velocity. And here you can see the waves has some envelopes. The envelopes are moving. Also the amplitude are changing. So the envelopes of the peak values, velocity of these envelopes of the peak values are called the group velocity, and velocity of the each wave is called the phase velocity. So in waveguide we are interested in group velocities, because this case wave is traveled in a packet or packet of waves, and this packet of waves are called the group of waves, and we are interested in finding the group velocity. So now the wave parameter, wavelength. So we know the wavelength for unbounded medium. So you can write, sorry, wavelength for the waveguide is 2 pi over beta, and beta, you know, beta u. So beta is equal to beta u times this. So it is beta u times this, beta u times 1 minus fc over f squared. So now 2 pi over beta u can be written like lambda u, that is the wavelength in unbounded medium, divided by 1 minus fc over f square. The cutoff wavelength, the wavelength at cutoff frequency, you know, the cutoff frequency, the signals will not propagate, but sometimes we might need to know the wavelength for this. So it is u over fc, and you can find this expression. Now we have to find the wave impedance for TE mode. So for TE equations are these are the H field equation, Hz, and this is the EX equation, this is EY, Hx and Hy. So we write the expressions for TE mode. Now the wave impedance or intrinsic impedance is equal to eta TE is equal to Ex over Hy. So the x component of E field and the y component of H field. So if we plug in this value for x s in the frequency domain, this is also already in frequency domain, and then Hy. So if you would want to write the s, you can drop this s. So you get j omega mu over gamma, and gamma is equal to j beta. So then cancel out this j, you will get omega mu over beta. And beta is beta u like this. Then beta u also can be written like omega mu epsilon mu. You will get then square root of mu epsilon this. And this is the wave impedance or intrinsic impedance for unbounded medium, that is eta u, and divide by this. So for transverse electric field, you can find the wave impedance is the unbounded impedance divided by the factor of this. For TE mode, you also can find the E field over the S component of magnetic field, Y component of E field, divided by S component of magnetic field, but there is a negative sign in the formula. So if you take S component of E, Y component of S, then this ratio will be positive. But if you take Y component of E and X component of S, then you have to multiply with the negative sign. Now for TM mode, the intrinsic impedance, we are taking the TM mode expressions here, this EZ, then EX, EY, ASX, ASY. This expression we already solved in previous lecture. So then the impedance, we can find AS, ES, ASY, and the expression is like this. So NU, this. So you can easily identify the difference between TE and TM mode. So in TM mode, the impedance will be smaller, much smaller than the unbounded impedance. But for TE mode, the impedance of the waveguide will be higher than the unbounded impedance. We also can find the impedance by taking the Y component of E and X component of H, but don't forget to put this minus sign here. So this is the wave equation for TE10 mode. So we tailored the wave equation for 10 mode. 10 mode is we are putting m equal to 1 and n equal to 0. So if you put m equal to 1, then this value will be pi a over x, and n equal to 0, this value will be 1. So you get Az equal to this. Now you can find Ex component. So if you put m equal to 1 and n equal to 0 here, sine 0 is 0. So everything will be 0. So you get here 0. If you find the y component, then it is sine and cosine. Cosine 0 is 1, so this is 1, and this sine 0 is, sine 1 is m pi, so you get some m pi, and this one. A6 has sine m and cosine n, so you will get A6 value here. HY has cosine m sine n, as n equal to 0, so sine n becomes 0, so it is 0. So you see here for TE10 mode, you have AZ, you have EY, and you have ASX. So basically, the waveguide in the microwave lab operates in T10 mode, and we have the devices like SWR meter or power meter that can measure only the electric field, not the magnetic field. So we basically measures the E component of the electric field, or that, because there is no X component for electric field, and there is no Z component either, because this is TE mode. So TE mode has no EZ component. So you see we have only one component of electric field, that is the Y component, and we measure this. And the expression is here. So this is the expression for EY. Now if you take this EY component and simplify further, we have a negative sign here, negative sign. So we can write it like this, like expand this like this. So you will get 2 this. So if you expand this, you'll get 2 sine n pi x over a, and then you can cancel out this 2 with this 2. This will be like this. If you just take this pi z inside, then you can write it like this. So you'll get uy equal to this. So that's like 2 waves here. One wave e to the power beta z with an angle theta z theta. Another wave has the angle z theta. So these two waves basically propagates together in a form of group. That's why we find the group velocity. So these two waves makes a group, and we find the group velocity. So for rectangular waveguides, you have to solve this type of problem. So you see here a waveguide is filled with perfect dielectric, permittivity epsilon and permeability mu, and the mode of Mn. The phase constant is given by this. We have to derive the cutoff frequency expression. So you see the phase constant is given. So at cutoff frequency Fc, the Fc, what will happen? Both alpha and beta will be 0. Alpha equal to 0, beta equal to 0. So if you put beta equal to 0 here, and the at cutoff frequency omega will be omega c. Omega is equal to omega c. So now at cutoff frequency replace this omega equal to omega c, put p equal to 0 and then solve the expression for fc. That's the expression for cutoff frequency. Derive the expression for phase constant in terms of cutoff frequency. We already showed in the slide how to find the phase constant beta in terms of cutoff frequency. And then it is said that a 5 times 2 over 5 centimeter waveguide. So that means A equal to 5 and B equal to 2.5. Waveguide filled with the lossless non-magnetic dielectric of this epsilon r equal to 9. 3 lowest mode can propagate through the waveguide. So you have to find the cutoff frequency for modes like TE on 0, then you solve for TE0 on, TE1 on, TE1 on and TM1 on same thing because the expression is same. TM1 on, TE20 and TE02. So solve for these 1, 2, 3, 4, 5, 6 modes. So among the 6 modes, these two have the same cutoff frequency. Basically, you are solving for 5 modes and then find the 3 lowest frequency, 3 lowest cutoff frequency. So if you find this one, this one, and this one has the lowest frequencies, then these 3 modes will be possible. So 3 will be the lowest mode. So among these 5 results or among these results, which one has the lowest frequency is called the dominant mode. Let's say this could be the dominant mode because it has the lowest cutoff frequency. The frequency range where only above 3 modes are possible. So you can find the frequency of this. Let's say this is the lowest frequency and this is the highest frequency or this is the highest frequency. Then you can find the frequency range, operating frequency between this and this. So cutoff frequency of the lowest one 10 and the cutoff frequency of the third one. So let's say third one is FC 20. Let's say I don't know which one. So you can find this and find FC20. So their operating frequency range will be this. Higher than this but lower than this. Then 3 mode will be possible. Okay, not lower than this. So you have to take the fourth one. So 1, 2, 3. So maybe this is the fourth one. So you can write 4202. So then it will carry the 3 frequencies, 3 modes. So there is another example here. So maybe very similar question. So you can practice this one. And this is also a problem from the textbook. And you can solve this problem.